Hello everyone and welcome to this webinar on our use case, the CP factory. My name is Vincent Rofaz. I'm an industrial engineer and I'm a research engineer for the CECOTP, the research center of the Province de Liège, and I'm working with the HEPL on a project called EMEA Digital Twin Academy. This use case consists of the digitalization of all the stations of the cyber factory at Technifuture. The project is being developed from a partnership between Job at Skills and Technifuture, who are the owner of the CP factory, and between HEPL and CECOTP, which are the school and the research center associated to the Province de Liège. So the CP factory, or Cyber Physical Factory 4.0 at Technifuture, is made up of different machines carrying out an industrial manufacturing process. So we have assembly by robot, drilling, quality control, storage, and so on. The CP factory reflects the new network production method of Industry 4.0, and it offers a modular system to build a smart factory for teaching and research purposes. The CP factory illustrates the practical implementation of a fully connected factory and can be used to represent the entire value chain: assembly line, logistics, production planning and control, MEMS, quality control. Now, the CP factory is made of 10 different modules. It consists of a small factory producing smartphones. There are three main components: the front cover, the back cover, and the board that can receive up to 2 fuses. And during the process, the product is being transported from station to station on conveyor and on a pallet and the carrier. So during this project, several solutions softwares have been tried to find out which one suits the best for the application. We had tried Factory.io, Siemens NX Mechatronic Concept Designer, MATLAB Synscape Multibody, and ROS. The digital twin was developed after reviewing the best software for the application. So for our use case, unfortunately, we didn't have the time to digitalize all the stations. We will not take the time to explain all the reasons here, but here are 5 stations we have digitalized: the pallet storage, the drill station, the camera inspection, the automatic magazine, and the output station. We will review them one by one, except the camera, which is not really interesting in this case. The first station we realized was the drilling station. The first step was to realize the conveyor with the stopper. So this part is the same for every station, except for the ones with the bypass. And to realize the conveyor, we use a transport bent, and for the stopper, we use a sliding joint. The drill application itself was one of the simplest. This only contains pneumatic movement on the X and the Z axis, and then we have the drills. So the pneumatic movement are realized with sliding joints, and the drill rotations were realized with the cylindrical joints. Collision sensors were used to detect the parts, and limit sensors were used to detect the position limits of the axis. Next station was the back cover magazine. So the pneumatic axis for the lifting unit was realized the same way it was for the drill. The more complex part was the back cover dispenser with the 2 layers of poles that open and close to let go one part at a time. There's a mechanical articulation transforming the direction of the actuator. So it's a pneumatic cylinder that goes in the x-axis. So to the right it goes out, and the articulation is between that axis and the power direction, which we see goes in a direction with an angle. And for that we define mechanical cams in MCD to synchronize both the movements of the actuator and the poles. So in this simulation we had also some work around the collision inside the magazine. So the covers in the stock are in contact with each other, but also with the magazine, in which they need to slide down. We're now able to run the simulation with 3 or 4 covers in the magazine, but the computation becomes too important if we increase that number. And the timescales drops, which decrease the reliability of the simulation. So there are still some improvement and optimization to do over that part, with different function on NXMCD to be tried. So we then simulate the pallet storage. So the storage contains 32 places where the pallet are stuck with or without front cover. So the picking unit, it's made of 2 servo axes, X and Z axis. There is 1 rotary pneumatic movement to change from one side to the others, and a linear pneumatic movement to reach the position. And finally, we have 1 gripper to pick the pallets. So it's possible to completely emulate the servo drive behavior with Siemens CIMET software, but we didn't have the time to try this feature. So in our case, we simply choose to command those sliding joints by giving an analogic set point from the PLC. And we use position sensors to send back the position to the PLC as an encoder would do. The rotary axis was made of a hinge joint, so there is not much difference compared to the sliding joint. Only difference is that the vector is circular. For the gripper, so there's a specific function in NXMCD for the gripper. So we need to define the fingers and the direction they slide. And this is what we use to set our pallet gripper. Then for the 32 pallets which are in collision with the shelf, there was a lot of computation for that. And to reduce that computation, we used what is called a bond zone. So it was created around the 32 pallets in the stock. And so this bond zone makes the pallet fixed until they are grabbed by the gripper. And we use kind of something similar when the pallet is dropped on the carrier. So they are linked together and the computation of the collision between them stops. So this is an optimization of the computation in the program. And finally, we simulate the output station. So we have a gripper collecting the final product, the smartphone, and the collaborative robot picking the product to store it in the box. So the x-axis is driven by a Festo controller. We had to simulate its behavior in a MCD. For the gripper, we use the same as for the storage station. So we define a gripper with finger, but for the robot, we defined also a gripper, but with a suction cup. And to drive the robot, so we needed to define all the joints of the robot, and then we used inverse kinematics. So we give points to the robots, and the software calculates itself the path. So this is how we did the robot. So a good part of the stations has been digitalized. Some will need some improvement optimization regarding computation load, and 2 big stations with robots still needs to be digitalized. Those 2 stations, they will add a lot of work because there are a lot of things to move, and the robots, as we have seen with the inverse kinematics, that requires a lot of time to configure. So it would also be interesting to assemble all the stations together and try to simulate the complete process, but this will require a lot of capacity from a computer, so we really need a supercomputer to do that. And yeah, that's it for conclusion.
You can access the training module via the link given. We've provided detailed step-by-step instructions for the sorting station. There are a total of 7 videos. How do you start the project? Physics, transport, joints, signals, sensor, and finally communication.